Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the traversal of a binary search tree, which I'm going to be referring to as a BST from here on out. Now, as a quick aside, if you are not familiar with BSTs or you don't feel comfortable with them, definitely check out the BST construction video that we have here on algoexpert.io. It covers everything you need to know about BSTs. But without further ado, let's dive into this question. Basically, we are told that we want to implement traversal of a BST using three different techniques: the in-order technique, the pre-order technique, and the post-order technique. And as we traverse this BST using these techniques, we want to grab all the values of the nodes in the BST and add them to an array that we then return at the end. And so here you can see I've written out the array that we want to return. If we traverse this BST here in order, this is going to be the array we want to return. Pre-order, this is going to be the array we want to return. And finally, post-order. Now, I will say that these traversal methods tend to be something that frightens people when they first learn about BSTs, because they're pretty hard at the beginning. Like it's a struggle to come up with how you do them, because you start to ask yourself, okay, how do I keep track of parent nodes? How do I keep track of child nodes? But it turns out once it clicks and once you learn how they work, they're actually exceedingly simple because they only take a few lines of code to implement. And so we're going to start with in-order traversal. And then once we figure out how in-order traversal works and gets implemented, the other two are going to fall like dominoes. They're going to be really, really easy, almost trivial. But so basically, in-order traversal, as its name suggests, wants you to traverse the BST in order, like as if you were sorting the BST in ascending order. That's how you want to traverse it. So as you can see, the answer here, the final array that we give, is a sorted array. And so it starts with 1, 2, 5, 5, 10, 15, all the way to 22. But so to put it in terms of a BST, in order always has you look at the left node first, then the current node, and then the right node. So let's start with a very simple example that I'll write in green. Imagine we have a BST that has a root node of 3, then a left node of 1, and a right node of 5. If we want to do in-order traversal on this BST, we call the in-order traversal on the root node, right, which is 3, but we start by traversing or adding the number 1 to our array, then we add the number 3, and then we add the number 5. That's in-order traversal, okay? And so now, if we were to add to this tree, let's add 2 more nodes, 2 child nodes to the node that has the value 1. And so we're going to have a left node of, let's say, -5, and a right node of 2. Well, in this case, in-order traversal is going to start all the way at -5, okay, because that's the smallest node in the tree. Then it's going to go up to 1, then down to 2, then back up to 3, and then down to 5. So the pattern that you can kind of start to see here is that whenever we are on a given node, we want to call the in-order traversal function on, or we want to, let me take that back. Before we talk about even calling the in-order traversal function, when we're at a given node, we just want to traverse the leftmost node, or the left node. Then we want to grab our current node's value and add it to our array. And then we want to traverse the right node. So using recursion here, we can basically say at any node in the array or in the BST, we can like say 3 things, okay? We start by calling the in-order traversal function on the left node of the node that we're at. Then we append to our array the current node's value, and then we call the in-order traverse on the right node. So I guess I'll write that down. For any node, we say in order traverse and I'm writing kind of pseudocode here, in order traverse on left, then array dot append current value, current val, and then in order traverse on right. And obviously here we're going to want to pass in our array to these in order traverse functions, but you kind of get the idea. And these are literally the only 3 lines or almost the only 3 lines that we have to write to make this work. Because what's going to happen is if we call, let's say this is our function, and we call it on the root node here 10. So I guess I'll even circle 10. We call it here. The first thing we do is we in order traverse on the left. Okay, so now before we even get to the second line here where we append the current value to the array, we start going down the tree. We call in order traverse on left, which is 5. Okay, so now we are in the in order traversal of 5. And the first thing we do is we call in order traverse of left. So now we go down to the 2. And before we append the 5 to the array, we call the in order traverse on 2. And then similarly here, we go down and we call in order traverse on 1. And before we append 1 to the array, we call in order traverse on 1's left child, which is none, right? It's like a leaf node. We're at the bottom of the branch. And so in that case, here I didn't write it in this pseudocode, but if we hit the end of a branch, a none node, then we don't do anything. But if our node is not none, then we in order traverse the left subtree. So now, since we hit a none branch or a none node, and we don't do anything there, well then now finally we can hit this line of appending the current value to the array for the 1 node. And so we can append to our array, if we write our array here at the bottom, let's write our array here at the bottom, we can now append 1. And now we start going back up the tree, okay, and back down then for the right child, because now we hit this line, in order traverse on the right subtree. And again, here we've got a none value. The right child of 1 is nothing. So we don't do anything, and we can start climbing back up, okay? Because now the entire in order traverse function on the 1 node here has kind of completed, okay? And so now we hit this line, array.append current value, on the 2 node. And so we append to our array 2. And then we hit this line of in order traverse right on the node of 2. And so we go to the right child of 2, which is a none value again. We're at a leaf. We're at the bottom of a branch. So we don't do anything. And then we climb back up now to this 5. And so just like that, you see, we can append this 5. Then we're going to go back down to the right child, which is going to be 5 as well. And then we're going to go back up to 10. So we're going to append 10. And then we're going to go down to 15. But before we append 15, we're going to go down to a none node, to a leaf node. We're not going to do anything. So then we're going to go back up to 15, append 15, and so on and so forth. And so that's how in-order traversal works. And it literally, the core logic behind it happens in these 3 lines of code, which are going to be almost identical to this pseudocode once we actually implement it out. And so similarly, for pre-order and post-order, all we're going to do is actually change the order of these 3 lines, because pre-order, the way pre-order works, is it wants you to append the current value to the array before you traverse the left and the right. So what we can say is that for pre-order, if I can grab kind of this middle line here, this is going to move at the top. And similarly for post-order, this is going to move to the bottom. Okay, and so this will make more sense when we write it out in code. But that is kind of the core logic behind BST traversal. And so now if we look at the space and time complexities, it's going to be the same for all three. The time complexity is going to be equal to O of n, where n is the number of nodes that we have. And the reason it's going to be O of n is because at the end of the day, we have to traverse every single node to add it to our array. So the time complexity is O of n. And there's nothing that we just do a constant time operation of appending the value to the array whenever we traverse the BST node. And then for the space complexity, it's also going to be of O of n, but this is a bit more involved here. The reason it's O of n is because we're creating an array of length n, where we're storing all these values. But if we weren't creating an array, let's assume that the function just had us print the value of the nodes, which wouldn't take up extra space. In that case, the space complexity would actually be O of, let me write it, it would actually be O of D, where D is the depth or height of the BST. In other words, D is the length of the longest branch in the BST. And the reason for that is whenever we call, the traversal function, like, here in order traverse, we are adding a frame on the call stack. Because when we call in order traverse on 10, and then we call in order traverse on 5, the in order traverse of 10 stays on the call stack and has to be kept in memory. And so, in terms of space complexity of this algorithm, the biggest number of frames that we're going to have on the call stack that are being used is going to be the number of the greatest or the longest branch of the BST. In other words, the depth of the BST. But again, this kind of gets nullified by our particular question, which asks us to store everything in an array, because this array is going to take up O of n space, which is, either in most cases greater than the depth, or in the case where a tree is literally just one branch, it's equal to the depth. But so that's how these traversals work in terms of time and space complexities. And now let's dive into the actual code implementation to really see their recursive beauty and how you can write them in just a few lines of code. All right, so we've got our in-order, pre-order, and post-order traverse functions defined. They take in a tree as well as an array, which is going to be an empty array. And the first thing we're going to want to do is make sure that our tree is not a leaf node, not node at the bottom of a branch, which has a none value. So we can say if tree is not none, then we can do some stuff, okay? But if it is none, then we can just kind of return the array. And this line, to be honest, will probably be useless when we hit a leaf node because we're not going to be using the return value of all the in-order traverse calls, except for the very first one, which is going to return the final array. But so basically, if the tree value is none, we don't do anything. Everything that we're going to write here on line 3, we're not going to do. But so if the tree is not none, if we are at an actual node, then for in-order traverse, we literally apply the logic that we wrote out in pseudocode during the conceptual overview, which is call the in-order traverse function on the left subtree, passing in the array. Then, once that's done, append to the array the current tree's value. And then finally, call the in-order traverse method on the right subtree and pass in the array. And so literally, it's this simple. Again, 3 lines for the sort of core logic, and then a couple of additional lines here for, to take care of the edge case or the base case where, we're at a leaf node. We're at the bottom of the tree. But so to make sure that this logic really makes sense, we can kind of dive deeper into how this works and reiterate what we said in the conceptual overview, which is we start by calling the in-order traverse function on the root node. And the root node most likely is not going to be a none node. And so because it's not a none node, we start by calling in-order traverse on the left subtree. And so before we even get to here, like before we even get to this line number 5, we're calling in order traverse on tree.left. And so, this is going to then call in order traverse on tree.left.left, right? The left subtree of the left subtree, and so on and so forth. And so then, once we finally climb back up to here, we've probably added a lot of values to our array. Then we append the value to our array, and then we do the exact same thing with the right subtree in order traverse on the right subtree. And finally, we return the array. And again, this is going to be useless for all of these sort of auxiliary calls to in order traverse. It's just going to be useful for the initial time that we call in order traverse and want to get the final array. Now for pre-order traverse, this is going to be very similar. We're going to have if tree is not none and return array. This is going to be the same exact thing. We have the same sort of base case. And then the only difference is that we're going to start by appending to the array the value. Why do we start with that? Well, because that's the definition of pre-order, right? We wanted first do whatever, we want to call whatever callback or do whatever functionality we want to do. In this case, appending a value to an array at the very beginning on the current value. And then we call pre-order traverse on the left subtree, passing in the array. And similarly, pre-order traverse on the right subtree, passing in the array. Now, as you might have guessed, post-order traverse is going to be very similar. If tree is not none, and then return array. And so here, we're going to start by post-order traversing the left subtree, tree.left. Then we're going to do the exact same thing on tree.right, and only after that will we append to the array the value. And so now, if you kind of go back to the conceptual overview and look at the example that we had, and look at the 3 answers that I had written out, and apply this logic yourself, right? Apply this sort of recursive logic yourself on that example tree and kind of work it out by hand, and you'll see that you get to those arrays. And so you'll see that initial that array that we had, right, or that BST that we had in the example, when we call post order traverse on it, the root node, which was 10, is actually going to be at the very end of the array because we're appending it to the array after all of the other post-order traverses are done. And similarly, for pre-order traverse, it's going to be at the beginning of the array because we're appending it to the array before all the other pre-order traverses are done. And for in-order traverse, it's going to be in the middle. And so all of these functions are going to run in O of n time, as we said, because they have, you're traversing every node at least once. And similarly, they're going to run in O of n space because, because we're storing everything in an array. Now, as I mentioned in the conceptual overview, if we weren't storing things in an array, if we had some kind of other callback function, or we were just printing values or something like that that doesn't take up additional space, then the space complexity would be O of d, where d is the depth or the height of the BST. So this is going to be the same space complexity and time complexity for all 3 of these functions, all 3 of these traversals. And I hope this video was helpful. I hope it was informative. I'll see you in the next one.